Hello, everyone. My name is Matthew Harold, and I'm here to talk about automated digitizer calibration using evolutionary algorithms as applied to gate models and gate simulations. So I'm a PhD student out of the University of Birmingham, working out of the Positron Imaging Center, and my research focuses on mainly using gate and gate models to optimize positron emission particle tracking experiments here at the Positron Imaging Center. So what is the gate digitizer and how does it work? The gate digitizer takes hits generated from Geant4 and applies pulse processing to these in a virtual manner so as to replicate the behavior of real detectors. This is the stage where things like readout, dead time, pileup, energy thresholding, and other aspects of the detectors are applied to the pulses generated and used to emulate how a real detector would respond. Gate models with calibrated digitizers can replicate the detector's response and readout scheme and trigger logic that would be found in the real detector, and is responsible for making sure that any data that you generate using gate is going to match what would be expected during a real experiment. So in the past, I've made a gate model with one of the detectors here at the Positron Imaging Center, the Phillips ADAC Forte, which is a dual-headed positron camera. And I've calibrated the digitizer of this gate model using an experiment that I ran here and processed using the NEMA protocol. Our detector in this image has a separation of 600 millimeters and the same in the experiment, but the heads on this detector can be moved from 250 millimeters out to 800 millimeters of separation. And with this digitizer calibration, which was done using what was known about the detector from a previous calibration or a previous characterization, and manually calibrating some aspects of the digitizer, the count rate versus activity curves of these two, the experiment and the gate model, match quite well. However, manually calibrating this digitizer model took a lot of time and effort to achieve this good of a fit. And because this was done by hand, this is also not guaranteed to be the optimal calibration of the digitizer model. Perhaps these curves could be a little better fitting to what was observed during the experiment. And even if you knew everything about your detector and its pulse processing, gate models are still a simplification of the complex pulse processing of the detector. For example, in this instance, we know that the detector crystals use Anger logic to locate where the hit was within the crystal, but that's not explicitly simulated within gate in this gate model. And further, we didn't do a simulation of the optical photons in order to simulate that as well. And all of these contribute to little inconsistencies between a real detector and what would be found in a gate model. Nevertheless, you can still achieve quite good calibrations of your digitizer to the experiment. However, but because of the time and effort it took to do a manual calibration, we propose that this can be done much easier and quicker using evolutionary algorithms. So what is an evolutionary algorithm and how can it be applied to the gate digitizer? So an evolutionary algorithm is an extension of natural selection of biological organisms. So if you have a population of individuals with varied genes and you give those individuals a selective pressure, some individuals in the population will survive or reproduce better than other individuals. And thus the next generation of individuals that are created will be better suited to that selective pressure because they're the ones who are able to reproduce. Similarly, this can be applied to simulations and gate simulations in such that if you have free parameters which you can optimize, these act as the genes of the population. You can initialize these digitizer free parameters with a random set of initial values and apply a cost function which evaluates how closely the simulations with some set of digitizer parameters perform, particularly how well the count rate versus activity curves are matched to the experimental count rate versus activity curves. And if you have a set of individuals within the population that perform better than others, you can use those good simulations to reproduce and mutate your parameter values into a new generation, which is better suited to matching that cost function, better matching to the count rate versus activity curves. And over time, what you would find is that as you reproduce the good simulations and terminate the bad simulations across multiple generations, at the end of this, your population of individuals would be much more suited to matching your cost function and will be much more closer to the count rate versus activity curves in the experiment. So to do this with a gate simulation, we're going to use the autonomous calibration and characterization via Evolutionary Software called ACCESS. This is a Python library that combines a evolutionary algorithm called Covariance Matrix Adaptation Evolutionary Strategy, CMAES, with an arbitrary Python script that is defining our gate simulation. And importantly, this doesn't just have to be a gate simulation. ACCESS is written in a way that it can take any arbitrary Python or any arbitrary simulation if it can be edited and manipulated using a Python script. So we take free parameters of our gate simulation, some parameters within our digitizer, and we say to ACCESS, these are the parameters that you can edit and change, and to launch simulations with a range of different values for these parameters, and ACCESS will launch them in parallel and evaluate the cost function after they're all finished, figure out what simulations perform better than others, and then relaunch new simulations for the next generation. And it does this in a way that it saves the data after each generation so that you can be able to return to your latest optimization state even after a core crashes or your whole system crashes, or if you are coming back to it sometime in the future, you can restart from any point that you would like. And ACCESS is created by a guy here at the University of Birmingham named Andre Nikusan. ACCESS is also a freely available library for you to download. It's on GitHub, our GitHub, at the link down below. So what we want ACCESS to do is we have a set of experiments that we've conducted with our ADAC Forte at 3 different simulations and looked at their count rate activity curves. Using the original manually calibrated digitizer, we can compare how well that performed to these experimental activity curves. And what we see is that while they perform okay, there's much room for improvement here, and it seems to suggest that we should calibrate our detector model further. So we're looking at the total count rates on the left and the true count rates on the right. And the cost function that we're going to define to compare how closely our simulations are matching to our experiment is simply the absolute percent difference between these two curves squared. And the squared term is there only to more harshly penalize simulations that perform worse than others. This helps the optimizer find what the optimum values are much quicker than if it were simply a linear relationship. So when we use ACCESS to calibrate this, we have to tell ACCESS which parameters to edit and which ones to keep as they are, and then set some lower and upper bounds for it to guess within. So we know from experiments and previous characterizations, some aspects of our detector, its energy resolution, the energy window, time resolution, coincidence window are all known, and we don't need to search for an optimum value for these. However, the singles dead time, coincidence dead time, pile up, and upper and lower energy discriminators have quite a deal of uncertainty on what they should be, and we're going to allow ACCESS to optimize these 5 free parameters. We're going to run all of our simulations on the high performance computing system here at the University of Birmingham. This is called Blue Bear. And for each individual in a generation, we're going to look at each of the 3 head separations and 5 activities within each head separation for a total of 15 gate simulations per individual. 100 individuals are going to be simulated in each generation, running on a single isolate core with 8 gigabytes of RAM each. And these 5 activities are chosen in such a way to look at both the low activity and high activity ranges of the count rate versus activity curve. So at the end of the ACCESS calibration, you get a plot that looks like this. You can see for each of the 5 free parameters that we're editing, initially, the guesses for ACCESS are very broad. It doesn't know what the right parameter value should be. But over time, the guesses become narrower and narrower, and the errors become lower and lower as it finds what the optimum values are. And as a measure of how closely we are to the end of this, the optimization on the right, the standard deviation is the standard deviation of the guesses that it's giving, so as to give you a measure of how broadly it's guessing. And this took 40 epochs to get to this point, which was about 3.5 days. So compared to the manually calibrated values, the values that our evolutionary algorithm came up with, some are a bit close to what we initially guessed they would be, 1.2 and 1.3. However, the other ones are quite far from those initial guesses. And these are simply what ACCESS has come up with as the best guesses for those 4 parameters. And we can compare from the manual calibration, how it performed to the experiment, and the gate simulated, or the ACCESS calibrated performance of the count rate versus activity curves. From this, we see that the true count rate is very greatly improved, and the total count rate does stay about the same, a little bit worse, a little bit better in some cases, but about the same. And we can quantify how well this improvement is. So on the left here, we have the manual calibrated values for percent differences. And on the right, we have the ACCESS calibrated percent differences. And at the end of the day, what we get is ACCESS is able to produce a count rate versus activity curve that has a mean error of about 6%, while the manually calibrated value, or Digitizer, has a mean error of about 10%, which is around what it was found to be in the initial publication of the gate model. There's pros and cons to using evolutionary algorithms. Pros are we got a much more closely calibrated gate model. And we did this in an autonomous way so that it was able to just be set up and run in the background while we're able to work on other things. It removes any conscious or unconscious bias of selecting parameters or parameter values. And it's a very exhaustive sampling of the parameter space. However, some of the cons are that it needs a very large amount of simulations in order to be able to find an accurate optimization. If you don't have access to high performance computing, you're probably not going to be able to use this because it will take a prohibitively long amount of time to do on a single core or only a handful of cores. And because this is autonomous, if you don't set the bounds of your search correctly, you could end up with parameter combinations which are non-physical, such as like a negative dead time or something like that. So while this was one specific case of using an evolutionary algorithm with gate simulations, there are some other ways that you could use evolutionary algorithms. While this is still improvement, you could use this same workflow for calibrating the digitizers of other additional detector models. And that would be very interesting if anyone has a digitizer model they're struggling to calibrate. I'm open to working together with you to apply this workflow to that. And I'm happy to use the supercomputing system here to run the simulations for that. Additionally, one thing that you could do in the future is you could begin to optimize parts of your experiment, things like your source activity, the time of your acquisition, and the placement of your source or patient within the field of view. However, you need a very well-defined cost function in order to evaluate the performance of this. Something like image quality is obviously going to improve with time, but you'll need to define some sort of cutoff where you define it's not getting significantly better after a certain point. Or something that would be very interesting is using an evolutionary algorithm to develop new detector geometries using a cost function that incorporates some desired characteristic of your detector, like sensitivity, spatial resolution, or peak count rates, and also incorporates things like the detector size or its cost, so that you can make the cheapest, smallest detector while meeting all of these design characteristics that you want. So that's my talk. Thank you for listening. If you have any questions, I'm here. And for any other questions, or if you're interested in applying ACCES to your own projects, feel free to reach out to me. And through email, I'll be here. And down at the bottom, you could look at the code for ACCES on your own if you're interested. Thank you very much.